Okay, so every time I'm saying like API casing chart you have to use or tubing chart you have to use. If you go to API like 5CT, that document, then you will find like tubing nominal diameter is giving 2.38, 858, many other big table is there actually. So I just taken one for example, and outer diameter is given in inch if you make a fraction. Okay, and the inner diameter size will be given, inside diameter size is given here. Okay, for example this. So several types of grade will be there, like J grade, C grade, N grade. Grade means different types of material combinations should be there. So based on that, you have to select your inside diameter. So normally like 1.995 will be commonly used, but other type of casing or tubing can also be used based on your requirement. The requirement based on your whether H2S gas is there, whether temperature high. So all those parameters you have to consider based on that. A, B, C, D, J, whatever, not A, B, C, D, J, C, N, these sort of classifications are there. You can select any one of the casing or tubing. So now we'll go to another big problem. It is given in Kermit Brown book. Okay, Kermit Brown, that artificial lift technology for artificial lift. Okay, so it is given like 8.5 inch outer diameter is given. Okay, so outer diameter is given 8.5 inch, 8.58 inch. This casing size is given, and tubing size is given 5.5 inch. Then depth 2200. So depth means here it is not written anything, but I think it is vertical. Let's say use vertical wellbore. Okay, so if we say horizontal wellbore, then we'll be giving vertical section or horizontal section length. Then in that case, whenever you are calculating hydrostatic pressure, then you are using TVD for hydrostatic pressure, but friction pressure drop will be whole pipe length. Okay, so this is your casing. Okay, so casing, this whole wellbore depth 2200 feet given, perforation 1900 to 2000. So perforation is done here. Okay, perforations is here. So this is a reservoir. So this is 1900. Okay, and this is 2200 anyway. And power source primary means the transformer is there, right? So transformer coils are there, right? So primary side given 12,500 volt. If this is primary, the secondary volt as per requirement you have to calculate. You have to calculate the turns also. Okay, static fluid level 500 feet on surface. So fluid level 500 feet given, 500 feet is given. Water specific gravity, gamma water is given 1.1, temperature 120 degree Fahrenheit. So wellbore temperature 120 degree Fahrenheit, surface temperature not given, so we assume the same temperature is maintained. Productivity index J is given 10 barrel per day per feet of drawdown. Here again you see this B per D they have written, so if we can write BBL per day also, that's okay. Surface flow line 2000. So this there will be, this is wellhead, from there one flow line is going 2000 feet. Okay, and it is 4 inch diameter, 4 inch, and elevation 30 feet. Elevation means this height is 30 feet. Okay, desired flow rate 10,000 barrel per day, and Q will be Q from wellbore to the surface, same flow rate will be there. So flow rate is 10,000 barrel per day. Okay, now you have to select a suitable artificial lifting system, suitable ESP system actually. I can give this question as a suitable artificial lift. So in that case you have to consider artificial lifting selection technique parameters. Here it is already specified, see right side, ESP you have to select. So what type of ESP will be there, what will be the power rating, what will be the flow rate, different parameters you have to find from this, whatever data is given. Based on that and you have to use some charts also, so that you can calculate actual what an ESP for your wellbore. Okay, so let's see. So first you have to calculate drawdown. Okay, drawdown means drawdown you get from Q by productivity index J, right? So flow rate, how much? Flow rate 10,000 barrel, already I told, right? And productivity index is given 10. So how much drawdown? Drawdown is your 1000 feet. Okay, this much of pressure will be gone. Now lift head. Lift head means 10,000 feet of drawdown, 10,000 feet drawdown plus 500 feet static head plus okay, static head and that drawdown, that is total 15 5, this is okay, 1500 feet. Okay, so pump should be set at 1500 or more actually, so that you can lift the fluid to the surface. So set pump at 1600. Why? You see this picture here. If I total pressure requirement from wellbore side, from surface side, total requirement you got 1500. Okay, so from surface if you are putting at 1500, then you have to give some margin. So margin is 100 feet margin they are giving. So pump you have to set from surface 1600 feet. Okay, and for no friction, no wellhead pressure, this pressure if your pump is developing, this will be okay. But you have wellhead pressure. How we are getting wellhead pressure? Wellhead pressure is equals to elevation component, elevation component plus friction, piping friction component plus okay, wellhead means elevation and piping friction. Piping means surface piping friction. So elevation is given 30. If you see the previous slide, elevation is given 30 actually. You see this, okay, here. And friction component. How to get friction component? This table actually you have to use. This table is there in the book, Kermit Brown. It is having x-axis and y-axis. X-axis shows how much flow rate. Okay, this is 10,000 barrel per day, and y-axis is frictional pressure drop. Friction pressure drop. Okay, and your surface piping is 4 inch. So 4 inch means this one 4 inch, a new pipe, it is written there in problem. So this is 4 inch new pipe line. So 10, if I extend this one and if I move towards this, so it will be 55. So it will be 55 per 1000 feet into total length of surface pipe is 2000. Okay, so this gives 140 feet. Okay, the surface 2000 feet pipe and plus 30 feet elevation is giving 140 feet pressure drop on the surface, well, on the wellhead. Now friction pressure drop in tubing. So friction pressure drop in tubing, P friction tubing. Okay, so it will be like if I see 5 inch tubing, 5 inch tubing is here. This is 5 inch tubing. So 5 inch tubing in 10,000. So 10,000 line is going here and 5 inch tubing coming here. So if I go this side, okay, it is becoming 18.5. So 18.5 divided by 1000 into 1600. 1600 why? Because already we said that pump you have to put at 1600. So total it is becoming 29.6 feet. Okay, for new pipe. If old pipe is there, then the friction value will be different. Then total dynamic head, equals lift, how much lift it is giving, plus tubing friction, PFR tubing, plus PWH. So total lift is 1500 plus 29.6 plus 140. So it is becoming 1670 feet. So this much of total dynamic head the pump should produce. Now to select suitable pump. So you have to go to table. Yeah, so casing size 8 and 5/8 inch. This Reda pump company, they have given this chart. So just to select, for practicing, we need to know how to use the charts. Actually, you can see this is pump curve. Actually, this is showing this HQ curve. This is efficiency curve, and this is HQ curve. This is eta curve, and this is power curve. Okay. So for 8.5 inch tubing, here it is 8 and 5/8. 8 and 5/8, it is written there, and it is 100 stage pump, 100 stages is written. Okay, and series 650 and RPM 3500. Because it is 60 hertz they are assuming, and 100 hertz, 100 RPM reduced because of your loading, and synchronous will be 3600, but because of loading 100 RPM reduced, so it is becoming 3500 for 60 hertz pump. Okay, and is x-axis is showing capacity. This is capacity of flow rate. Okay, so we have 10,000 flow rate. Okay, 10,000 barrel per day. So this is 650 series pump, and it is giving so if I see this flow rate is here 6200 about. Okay, so Q is becoming 6200 feet for 100 stages. Okay, so that means per stage flow rate, Q stage 1 6200 divided by 100, so that means 6.2 feet, not 6.2, this is 62 feet. 62 feet flow rate you are getting. Now number of stages for our case, so per stage 62 feet. In our case, total depth is 1670 divided by 62 equals 27 feet. Okay, so minimum 27 feet will be required for our case. Okay, normally you have to use more than that, because there will be some other losses you are not counting now at this moment. For this simplification, I have done this. Now you go to motor horsepower. So if I see motor horsepower here, the same chart, this is going to this one horsepower chart, motor horsepower. Okay, motor horsepower curve, and this is pump efficiency curve, or eta, motor horsepower. Okay, so if you go to right side, you can see motor horsepower, it is becoming 585 around. Okay, for 100 stages, 585 HP. So one stage 585 divided by 100, so 5.85 HP. Okay, horsepower. So but in our case, water specific gravity is 1.1 is given in the problem. So actually HP requirement will be 27 stages into 5.85 per stage into 1.1. So it will be 174 HP. Okay. And in this pump we have seen maximum his head horsepower is 600 actually. If you see the horizontal line is going to 600, means per stage 6 horsepower. Okay, if I use per stage 6 horsepower, then my total horsepower will be 6 into 27 into 1.1. So it will be 178. So for maximum power calculation we have to use 170 horsepower. So that much required, that is fine, but how much maximum possible, so that one you have to calculate. Based on that you have to buy your motor. Okay, so for cable normally the thumb rule is that 30 volt drop per 1000 feet of cable length will be okay. Okay, so in this case you have motor distance plus surface cable all together, actually you have to calculate and you have to see how much voltage drop is there. So they are assuming like 1670 feet your pump depth divided by 1000 into 30. So this much of, so 0 0 0, so 49.1 voltage drop, or about 50 volt drop is there, okay, through the cable. So if we calculate surface cable also, for example, it is going 50 feet about, you can remember this wellhead is there, then will be junction box, then be switch, right? So this total distance is 50, about 50 feet. So if I add the 50 feet, then my voltage drop will be a little bit higher, okay, because your switch box will have all the measuring voltage, current measuring and controlling equipment. So from there you have to see how much voltage drop is there through your wellbore. Now there are several problems in the book of Kermit Brown. Students are suggested to practice some of the problems, like similar problem, like say presently I am calculating this one using 60 hertz. Okay, if I change 50 hertz, what will happen? If I change my elevation, what will happen? If I change surface length, what will happen? If I change tubing or casing diameter, what will happen? Okay, if I change voltage drop to the cable, what will happen? What are the transformer size also you have to calculate actually. Pump efficiency, if I change, what will happen? So those questions can be asked. Now in the previous lecture I have seen separately pump efficiency calculation, this calculation. Now this whole problem integrates everything actually. Now you integrate everything. Now next thing is that ESP, where to use and where not to use. Okay, if you have crooked wellbore, crook means like this or like this or like this. Okay, small radius, big radius, different types of wellbore will be there, multilateral also will be there. So in that case actually ESP can be used. ESP can be used for the screw wellbore, because ESP vertical, horizontal doesn't matter, it will pump. Only the frictional pressure drop and other pressure drop, you have to calculate separately. Gas, 10-15% gas will be okay. Let's say 10% to 15% maximum. Okay, if you have more than that gas, then ESP will be having difficulty. Although you will have gas separated, but still it will have difficulty. Sand, small amount of sand is okay. Big amount of sand, it will be eroding the whole surface. H2S also again one problem will be there. H2S means corrosive gas, very highly corrosive. So if you have highly corrosive gas and sand also there, highly corrosive gas, it will be reacting on metal surface, it will create highly corrosive oxide. I think you have seen in previous lecture, metal oxide will form or metal sulfate will form salt, softer material. Okay, and if sand is there, let's say surface is getting some softer salt, metal, Fe plus H2SO4, FeSO4, Fe plus H2S, FeS. So ferric surface of sulfate or sulfide will be formed, that is softer than metal, iron. Now you have sand particle hitting the surface, this soft material will be getting removed. What will happen? The metal will get exposed to H2S again, hydrogen sulfide. And what will happen? Metal will be reacting again with hydrogen sulfide, again sand will hit, it will remove. So erosion and corrosion both will work together and metal will be degrading quickly. Okay, and at the same time you have cavitation issue also. Again there will be erosion, corrosion and cavitation all together will be multiple, more complex situation. Temperature, at certain temperature it will work okay, but because you have elastomeric seals and other thing and electric cable, so very high temperature it will have difficulty. But if some company is making proper insulation system in the downhole motor and cable, then things may be okay, but normally very high temperature people should not use. NPSH. So a centrifugal pump or ESP system, they need a highest NPSH among all the artificial lifting technique. For example, you have PCP or sucker rod pump here. So they need very smaller amount of initial pressure or suction pressure, but ESP needs very high amount of suction pressure. So suction pressure needs high. Okay, high temperature is low temperature, used for low temperature. Okay, temperature okay, high NPSH required. Offshore wellbore, ESP is not having proper very big surface unit, and on surface very small unit is required. For example, control box, junction box, transformer. So ESP can be used for offshore application also. And but normally sucker rod pump, normally people will be avoiding to use for offshore application because compact spacing and so heavy unit on the offshore is not good. Viscosity, very high viscosity, it will not work. For example, progressive cavity pump is there to help you for high viscosity, but viscosity small change because of certain water cut and low viscosity oil is there, so it is okay pumping. But very high viscosity thick fluid like grease, toothpaste, or very high 1 million CP viscosity, it will not work. Okay. Emulsion, it will increase viscosity, so again it will be having difficulty. Again, if you have multi-phase flow, if you have gas, then it will create multi-phase flow. Multi-phase flow also will have some difficulty in pumping, although it will have gas separator, but still there is limitation of pumping gas because of it will start cavitating or other issue will be coming up. And again, because this ESP, one stage, two ESP, multiple ESPs will be there connected, right? Stages 1, 2, 3, 4, 5. So one stage vibration or cavitation will be transferred to another stages. So if one stage is having, first one is having problem, that will be getting transferred. I mean, whole system will get too much vibration, it can fail also. Okay, so if I see artificial lifting selection technique, sucker rod pump, you have seen this is for low flow rate option, but ESP, it is high flow rate option. Sucker rod pump is having limitation, offshore application normally you do not use, but as ESP you can use for offshore cooked well. Gas, small gas okay up to 10%, but very high gas it will not work. Sand, H2S is enemy actually, because high speed centrifugal pump, when a sand particle is giving high speed, it will be hitting metal surface at very high rate, so metal erosion rate will be higher. Okay, and if you have emulsion, again viscosity will change, so pump performance will change. So if there is any change in the reservoir fluid property because of pressure change or temperature change, then you have to check whether viscosity also changing or not. If viscosity changing, or instead of single phase it is creating two phase. For example, your phase diagram is here and initial condition is here, and when it is at intake your condition is here, it is creating two phase. This is single phase zone A, B is two phase zone. Okay, so if fluid become two phase before entry to the pump, then there will be problem. So you have to use gas separator, but still there is risk of gas inside the impeller. Okay, especially the first stage is very important. If first stage is getting gas, then the whole vibration will be starting. But other stage, although gas will be there, but pressure will be increasing gradually. So that pressure also will be helping to avoid, or maybe it will be giving more mixture of things, and that will be less problematic. But first few stage will be more problematic if you have gas. This is the end of ESP system lecture. Thank you very much.